You might
What's the first one? Well, you put the, okay. So we're going to present this category theory applied to the Klein four parameter group and the universal rewrite system. We noticed that some of our diagrams look very similar to category theory diagrams, so we were very interested in seeing how category theory could be versions of category theory could be used for them. Sometimes you have to click that. It's very temperamental. Now, I did refer to the Klein four parameter group of mass, time, charge, and space. And that's the order in which we do them, because that's the simplest to the most complex. And we've not mentioned the fact that we had a universal rewrite system. It's a very simple process for doing this, to generate these parameters and other things. The universal rewrite system just generates, essentially, in the mathematical sense, it generates Clifford algebra, but it doesn't only generate that, but it does generate Clifford algebra. And you can do it in a one-line program, as we did in Mathematica. And we noticed that both the Klein four group and the rewrite system could be used diagrams that are very similar to those of category theory. Now, each of the parameters, we said enough, okay. Each of the parameters has a characteristic algebra. And I mentioned that before. You've got mass is scalar, time is pseudo-scalar, charge is quaternion, and space is complexified quaternion alias vector. If we combine those into as independent units, so we don't take them the lesser units as parts of the big ones like the vector, we take them as separate, we combine them all using independent units, we get a new Clifford algebra, which is two orders higher than vector, and it's the one I've just been using, the complex double quaternion vector quaternion or double vector, the 64-part algebra. We have proposed that nothing in physics lies outside of this group, and that the totality of characteristic over the whole group is zero. And this provides a zero stable structure, while the algebraic terms that generate them form a progressive structure. So there's a difference. You can take the parameters having properties, and they've got a zero structure. If you take them as algebraic, then you've got a progressive series from the lowest algebra to the highest. And we'll show that in a minute. And what used for that is the universal rewrite system. And so this generates the sequence from zero as a starting point, and you get this one result is the infinite Clifford algebra sequence, starting with real numbers, and then you incorporate eventually multiple vector systems, alternately in complexifications of them. The first four steps create the Klein four group, and then it goes beyond it. So this is the Klein four group, and I say these properties come from from the algebra. These properties are ones that I worked out many years ago as being the most fundamental, but they come from the algebra. The real and the imaginary is obvious, that's algebra. It's simply 1 and I. The continuous and the commutative and discrete and anti-commutative, that's all about dimensionality. Only dimensional things are discrete in this way of thinking, and non-dimensional things are continuous. So those come from the vector system, or the quaternion system, three-dimensionality. So this is distinguishing three-dimensionality from with no dimensionality. The first one, conserved and non-conserved, that's not obvious, but that actually is subtly due to the fact that there's an extra complex I term.
Presence or absence of
presence. So mass doesn't have it, time has it, charge doesn't have it, space has it. So you can see that space and time are the ones that are non-conserved because of this extra I. And you can get a backing from that from Clifford's own paper, which we did do.
Yeah.
Do you want to take over?
Yeah, so I think that this, given that we've kind of sussed out this category structure behind the universal rewrite system and the Klein 4 group, I would like to point your attention to the fact that I'm gonna let you be I'm gonna rename this whole situation as a category U, and that's going to be composed of two different types of. I'm going to divide up the groups into properties and anti-properties, and this is the property kind where you have the positive, where it's the like the positive version of it. And so if you move on to the next one, it can be all arranged in algebraic form. The previous, when these parameters can be arranged algebraically. Now, the group, if you constitute it this way, it can also has a dual structure. This can be found by switching the signs of one of the symbols X, Y, or Z, or all of them all together. And if you take one symbol and suppose it to be separating real algebras norm 1 from imaginary algebras norm -1, then something like this happens in effect. In the Dirac equation, there's like a reversal that Peter has discovered between the dual and the dual Dirac equation and the normal one.
I may say so. The reason for that is that you've got an extra quaternion in front of them that changes the sign.
Yeah. So yeah, this is basically the dual.
The one egg is cooked.
Okay, so it's kind of hard to explain a little bit, but if we let the objects of the category U be mass, time, charge, and space, and then let the properties be X, Y, divide up the properties into two groups, K, which are positive, X, Y, and Z, and K op, I'm going to call that just K op for just the dual, be -X, -Y, -Z. And you let those be the properties of the same objects, mass, time, space, and charge, then you can treat, there's two ways you can look at the morphisms between these. You can treat them as reflections, like of a cosine of, but reflections of a specific kind, cosine of 0 or 180. And you can also treat them as a binary product. So that's what I've shown here in the first column. I've got a group operation of any of the properties multiplied by themselves, and then the reflection, the corresponding isomorphic reflection similar to that. Also, if you notice that 90 degrees, if you conclude 90 degrees, you're outside of the, you don't get closure. So that's sort of like, you want to think of it that way, that's sort of like forbidden. And all these arrows and these, there's going to be another diagram that's going to show the arrows, but they're all isomorphisms. And this is the same, similar arrangement, except with the K-op. So you've got the same parameters, mass, time, space, and charge, but you've got the reversed rules going back and forth. So that'll be evident in the commuting square. So this is the commuting square for the properties. And like I said, you've got binary products and you've got their similar corresponding reflections. And you can see these arrows are going both ways. So that's like isomorphism. And so these have the same type, same size, at least the same size. So, and this is the dual, the other where I've divided the X, -X, -Y, -Z, and they're reversed arrows and everything. Now, moving on to the universal rewrite system of the category U, the algebras can start basically the first half of an open, infinite sequence of growing algebras. So again, like I said, if you take these definitions of mass, M, time, charge, and space, then you can see that this commuting square is, I'm not quite sure, because I'm not an expert in category theory, but I think it is a significant or pretty much a standard, probably standard commuting square. So you're going from mass, you can go from mass to time, and you can compose those, and you can go from time to charge, and then to space and compose those. And if you notice that each of these compositions, if you look at the arrows of the rules, the I1 is basically just taking the operators, sorry, the elements of mass and multiplying by I1. So if you just take mass and multiply by I1 as a tensor product, you should get time, which is the next one op, I1 and I1 op. So each of these operators is taking you from a smaller algebra to a larger algebra. And then the one from mass to space is going to be like the composition of the whole thing. So the arrow mass to space will be kind of like a free functor, but I'm not sure I could be corrected on that. And it's going the other way, reversing the arrows. Same thing, you've got the same parameters. Both the dual and the regular parameter group share the same identity, but they do have the reversed arrows and reverse functions. So the arrow space mass could possibly maybe be the forgetful functor. Correct me if I'm wrong. And this is very abstract, but it is what's happening. The closed cycle of the Klein-Form group represents a scale invariant repeating unit. Like as you go down this I'll call it a free functor, as you go from mass to time to charge to space and on to higher orders, you get this repeating structure of mass, time, charge, space. And I'm also going to say the free functor is not reversible, though in Clifford algebra it is. So you've got this kind of opposing characteristics. And then this is what it can look like. This is like if you look at the square, that's like the repeating structure, but you can go on and on to higher orders. And conclusion would be basically that when Clifford created Clifford algebra, he had in mind Hamilton's quaternions, closed cycles, and the idea of extending Grassmann's linear progression from the linear algebras up to a higher progression. So he seems like he combined the two and came up with a hybrid kind of system that's like commutative, that alternates between commutative, independent quaternion cycles and partial quaternion cycles. And so while the Klein-Form group is a closed cycle, which produces the nilpotent structure of fermions, which Peter was talking about in the previous talk, the rewrite structure is a linear progression. And we have a one-directional category theory diagram for the Klein-Form group, which has a classic form when applied to the algebraic structures, and which suggests the predominance of associativity, as in quaternions and Clifford algebras. However, when you use physical characteristics associated with algebras of the parameters, both directions are possible, and we can consider using the forgetful functor as a joint to the free functor. These are just some of the possible directions that category theory could seem to be suggesting itself in our system. Yeah. So the universal rewrite system is of course a pure free functor, but it can generate a increasingly progressive complex sequence of growing out of larger algebras. And it also can go back the other way using I think what we would call the free or the underlying functor. And it's the combination of that progressive sequencing with recognizable fixed patterns that makes scientific observation and theory possible. So thank you very much. Any questions? Yes.
Yes. So as you transition between those four major states, as they correspond to physical processes, so you mass to time, time to mass.
Yeah.
Are the corresponding physical process for each of those?
I think we have master time and things like that because you've got constants which connect them.
Right.
So, for example, you can have charge and mass connected by the two Coulomb type laws, the Newton's law and Coulomb's law. So that will connect your mass and charge.
Yeah.
You've got equations with fundamental constants which connect all of those and their inverses. Because one of the things about the parameter group is that each element is its own inverse.
Right.
So
I
you've
should have
got
mentioned.
mass in the inverse of time.
Yeah.
That's really quantum theory. That's where it comes from.
Yeah.
And you've got space and time connected by velocity of light.
Yeah.
So there's the fact that there are fundamental units, 3 or 4 fundamental units which connect everything together, is because of that, because you've got connections.
Are the ones identity functors then?
Yes, yes.
Okay, so that would imply that you've got a way of addressing that category. It's an identity functor.
Right. I
So
think
does it mean it's Cartesian at all?
I believe it is, but
Yeah.
I'm not certain.
I'm fairly certain they are.
I'm sure it is.
Yes,
Yeah.
because you would need that to be able to put in an identity functor.
Yeah, I
Yeah.
think they are
Yeah.
Cartesian.
Yeah, that was,
And I think these constants show that they're not an identity.
yeah,
Because if you got a fixed value for something, then it has an identity.
yes, identity is a very important property in category.
And this connects with that being equal to its own inverse, or
Yeah,
relatable to its own inverse.
Yeah.
That is an aspect of that Klein-Four group as represented here. That each is its own inverse.
Yeah, that seems to be a key feature.
yes, I think it obviously would be nice, wouldn't it, to define free and underlying functors for each direction.
Yeah, But I'm
I've
not
tried
sure.
doing that.
I'm not sure what I'm doing. Really, don't know for
You
certain.
just need an arrow in the other direction.
Oh, we got arrows in the other direction.
Yes, you have, haven't you?
Because you can use the forgetful function to go
Yeah.
backwards.
Yes, that's what I mean, the
You can-
same thing, forget.
You can drop your arrow, you can drop your vectors down to quaternions.
Yeah. That sounds very promising.
So that, I mean, the ones with the double diagrams there,
Yeah.
you go back to those at the beginning.
At the beginning. Yeah.
But the
Those
gaps are
there,
underlying are the same.
you could treat that diagram in that way.
Yeah. Yeah,
And you've got both ways in the same diagram, and this is what the group tells us that you can do.
yeah, no, I think that's very promising as a category diagram.
I'm sure that category theory does work for you.
Yeah, that's sort of what you call a natural category.
Natural
There's it couldn't.
Natural in the technical sense as well as the
We,
physics sense.
we've seen diagrams in your papers looking something like this.
Yeah,
Yeah.
yeah, that's right. No, I think that's promising.
Thank you. Does anybody have any other questions they want to ask?
Just to make a contribution, I'm not very good at category theory, don't know much about it. The group, what you call the Klein group, is known in finite group theory as C2 cross C2.
Yeah.
It's just two C2s crossed together. It's the inner automorphism group of the quaternion group, and also of the order 8 quaternion group, and of the order 8 dihedral group D4. The order 8 dihedral group D4 has 4-dimensional representations that give us space-time, and the quaternion group has 4-dimensional representations that give us the electron and neutrino field. As you add another C2 onto a group, C2 cross C2 cross C2, you get your 8-dimensional flipped algebras. You add another one, C2 cross C2 cross C2 cross C2, you get 16-dimensional flipped algebras, and on you go up and up. I'm not really certain about it, but I suspect the 8-dimensional C2 plus C2 plus C2 is the inner automorphism of groups like the higher order dicyclic groups, higher order quaternion groups, and the higher order dihedral groups. Whether that's of any relevance to category theory.
I don't know if it's relevant to category theory, but it's certainly relevant to what we do. Certainly the C2 business is relevant
Yeah,
to what
that's
we do.
features very much so.
But certainly the Klein group does include 4-dimensional space-time and the electron and the neutrino fields.
I was amazed to see the Klein-Four group using solar automata by this guy called Mainzer.
Mm.
And he gave a talk at Delft in 2013. And he didn't stay around for questions. He just cleared off after his talk. Unable to talk to him. And eventually located a book by him, which it had it in. And I thought it was exactly what I thought it was. It's the same group as you get when you do
Like a discrete
CP2
version.
symmetry and identity. you do identity and CPT symmetry, which is like a sort of a bit of the
Yeah.
space-time Moschel graph group. You get the applying 4 pattern, and his 4 cellular automata, he said these are the only 4 which are universally Turing compatible.
And there's give long range
You know,
stability.
264 basic cellular automata, and just 4.
Mhm.
I think it's 260.
That's not-
Just 4 have this universal Turing compatibility, and he was able to relate these as an analogous process to the C, P, and T when I read his book, and so I could see why it worked. But it's just struck me as being very interesting that was true.
Yeah, it was like a discrete version of this natural,
And yeah,
and discrete for digital.
and I was amazed to see that 64 units, and you just say, well, what else has got 64 genetic codons?
Mhm.
And in fact, they are the same 64. You can show they're the same.
Mhm.
And we showed that they were the same, and we showed that the same patterns came up. The 5-fold symmetry you get with those objects, the generators, you also get that in the way the structure of DNA actually operates.
Right,
It's on a 5-fold axis.
right, and you even see the pentad in it.
Yeah,
You
you
see
see
the-
the penta.
Yeah. So, any more questions? Otherwise, I'll close down. Okay. I'm closing down.
Have there other people got any questions?
Oh, does anybody have any questions there in Zoom? No,
Not very quiet.
no more questions, okay. Easy for me.
That's a successful lecture if you've got quite.
See the successful.
It's either totally brilliant or totally terrible.
Okay, I'm gonna stop recording now.